This section is really a lot of review of most of the topics covered in the intro and in the first part of the markets course. It just kind of walks through everything on a single example. This also uses a synthetic case, kind of like the examples that we did yesterday, but it's one that's on a California. And the whole process of this topic goes through kind of a step-by-step of one example, start to finish, doing things like limit monitoring setup, AGC setup, looking at generators, loading cost models, doing all that case development work prior to actually doing the OPF and then doing the OPF itself. Within the OPF, we'll look at different permutations like using a super area versus individual area control. Also looking at unenforceable constraints, doing load dispatch or curtailable load modeling and things like that. And then there's an appendix also that's really just a different example. And I'll probably just walk through the slides and not go through the details. It goes through a lot of things that are very rarely encountered, like strange issues with reactive power and strange issues with topology and things like that, that can just cause overloads that aren't real overloads that you want to focus on. Part one looks at the sample California study, and just as an overview of what we're going to do, we'll do a lot of kind of what I call case development, which is just like the set of actions that you take from initially opening a case before you're even ready to run the OPF. And there's usually quite a bit that can be done. A lot of it's repetitive and can be automated through auxiliary files if you're always doing the same steps over and over again on different cases. But it's good to know what all needs to be included in that so that you make sure that that's part of your process. Often on a very large case, at least in North American cases, unless it's ERCOT, usually you're not studying the entire footprint of what's modeled in the case. You know, in this example, the case will have the whole western part of the U.S. in there, but we're only going to study the California footprint. We'll set up our limit monitoring settings, set up just our area zone filters and things like that, just to zero in on the part of the system that we want to study and make sure that everything's aligned with that study footprint, like, you know, what the OPF controls are, AGC settings, and have our limit monitoring settings match that footprint so we're not trying to relieve constraints in Montana with generators moving in California, things like that. Part of the case development is also looking at or loading cost curves. Usually if you're starting from a raw file or other provided cases from industry, they're generally not going to have bids or things like that in there. So we'll put those in and we'll take a specific approach for how we're going to deal with hydro units. And there's different ways you can do this. There's no right or wrong answer. There's nothing in the software that optimizes hydro dispatch because it's typically, you know, longer term issues. It depends on variables that aren't part of the model. You know, things like available water supply, which is based on snowpack a lot of times in the West, and reservoir levels and all kinds of things that need to be coordinated to dispatch hydro. So it's not, we don't put in a thermal bid, but we'll set a bid based on the unconstrained lambda within the area. So we'll basically be bidding it in like a peaking resource. Then once the hydro is part of the dispatch, then we can solve a full transmission constrained OPF with the hydro being AGCable. And then just kind of step through different permutations of things that we might want to change. We're going to make this example quick. We're not going to spend a whole day on it, but obviously it's if you're grabbing a new case for the first time and you haven't worked with it before and you're not familiar with all the nuances of it, you could spend a long time on it. And if the case is extremely congested, initially you're not necessarily going to get a solution that relieves all the constraints. So it's important to kind of understand which constraints are important and which ones can be relaxed or ignored. Like I mentioned earlier, unless it's an ERCOT case, you're probably not going to like slap the whole system on OPF control because that doesn't really make sense. That's really not how actual systems are operated. we're just going to make sure that, again, we're focusing on one part of the system and ignoring the rest, or basically leaving the rest of it on participation factor control so that it's still dispatched and solved, and we're still getting good models for the system behavior at the boundaries, but we're not diving into the details outside of the part of the system that we really care about. So we're going to start actually from a raw file, which, would kind of mimic what a lot of people in industry do, because you're starting with a new model that's maybe updated on a daily, weekly, or monthly basis or something like that. And then I'll go to File, Open Case, and we'll switch the file type in the lower right to the PTI raw. And then scroll down. Yeah, it's the active SG 10K. It's got 10,000 buses. So we're going to go through some initial setup, and these settings are also can be loaded from an auxiliary file, but we'll go through some or most of it manually, just kind of as a review for looking at solution settings and limit monitoring settings, things like that. But the problem that we're going to frame is that we're going to look at within the California footprint, there's 5 separate control areas, and it has 1,100 or so generating units, with 850 of those, 52 of those committed. And initially, we'll see that there's 7 branch violations. And here is the OneLine diagram. So we'll need to open that. When you open a raw file, it doesn't automatically open a OneLine diagram, because that has to be saved with the PWB, that information. So open OneLine. It has the same or similar name line with California also. And the difference between that is this OneLine diagram just makes use of things like emphasis, formatting, emphasis filter, dynamic formatting. There's some dynamically sized pie charts, and also the lines that are overloaded are blinking. So I zoom in that area, and I can see lower voltage stuff is de-emphasized, so it's high voltage grid that's emphasized. And of course, just as a matter of review, we could go into our OneLines ribbon and then OneLine options and see that there's an emphasis filter that's active right here. And if I click on that, it just it grabs everything, every object type, but only looks at areas 3 through 7, and only looks at 200 kV and above. Anything that's outside of those areas or below 200 kV is kind of faded to the background, and of course you can adjust how much that's faded. And then just cancel that. And then we also have I go to the OneLines ribbon and open dynamic formatting. I can't remember if this is on the active OneLine or the whole case. It looks like it's an active OneLine only. So we go to dynamic formatting for active OneLine. And then here's the description of what's going on with the formatting. It's taking any branch that meets the filter overloaded lines and changes it color, changes the thickness. So there's also some saved views on this OneLine. If you go to the save view list, there's one for California, there's one for Cobb for California-Oregon border, and one for different metros, LA and San Diego, also zooming back out to the entire West. Okay, so the first thing we'll do is we want to make sure that we have a solid power flow. I think in this case it's straightforward. In some cases, you may need to do things like shut off AGC and shut off tap changing transformers and things like that. But the first thing we'll want to do is make sure that we can achieve a power flow solution before we do anything else. If we can't, then nothing else that's done later will be any meaningful. So yeah, I just opened the message log and clicked the solve power flow from the quick access toolbar up here and just made sure that we get a solution. And then we'll go into various menus to set up things like area zone filters and limit monitoring settings and things like that. So from the Model Explorer, we can just pop open the area zone filters. And this case is set up so that most of the areas are defined by state, but then there's 5 of them just within California. So in the shown column, I'm just going to toggle everything to no, except for 3 through 7. So I'll flip those back to yes. And then if I close that, then of course my displays are normally going to default to just showing what meets those filters. You can, of course, override that with this filter drop down right here. But if I look at my list of, let's say, generators, I can see how many are in the study footprint and which ones are committed and which ones are not committed, open or closed. And of course, I don't have any cost models. When you open a raw file, that sort of information is not going to be in there, but we'll load that later. We're also going to put areas 3 through 7 on optimal power flow control. Area 9, we're going to turn off of AGC because it contains the island slack bus, and the other areas we'll put on participation factor control. So if there's some adjustments due to losses or just different flows looping through the system through other areas and the generation needs to adjust, then it'll all adjust across the area and not just at a single point in an area slack bus. Go to the list of areas in the Model Explorer, and they're initially all off of AGC, and we have area control errors that are pretty significant for some areas. Actually, the ones within California have some pretty significant differences. So we don't want to solve the case on AGC without zeroing those out. Because if we try to do that, then it's going to move a whole bunch of power around to try to zero those out and change our starting point. So anyway, but before we do that, we'll just go into the AGC column right here and we'll set everything to participation factor control because that's what we want most of them to do. And then in areas 3 through 7, we'll change it to optimal power flow control. And then in area 9, we'll take it off of AGC. We wouldn't want to solve the case right now necessarily because that would cause a lot of power to be redispatched. So we'll just come over here to the unspecified megawatt interchange and make this match the actual megawatt export. So we want this column to be equal to this column right here. So we can do that just by setting all values to field. We can go to set. You might have gone through this during the case info topic, this tool right here. Yeah, make sure you're in the unspecified column and then set everything to field. And then we'll just kind of scroll down to the interchange. And then choose the actual megawatt export. And then when we do that, then we should see all of the ACE values go to 0. And at this point, we should be able to solve the power flow again without it moving from where we have it, because we've got it in a solid state right now. So yeah, it does some outer loop checks, but then it finds there's really nothing that it has to do and everything's within tolerance. So for our initial dispatch, we didn't really nudge the power flow at all from its starting point. But when we do the OPF solution, it is going to move, but we want to make sure that certain units are taken off of AGC so they don't try to dispatch those. And then we'll also need cost curves eventually loaded for the other types. So we'll go to our generators. Well, actually, yeah, to know what these types are, we do have to load those in from an auxiliary file. So actually, I'll do that first. And it might actually make the AGC settings from that. So we can look at our generators in the Model Explorer, but that's not necessary for loading the auxiliary file. We can go up to the Quick Access toolbar and tell it we want to load an auxiliary file and go into the M8 LMP multi-area and then choose generator cost models. And what this is, I'll just open this in a text editor here. This is going to load in a bunch of piecewise linear models for anything and it's going to designate fuel types also. Things that are not thermal. So down here, anything that's at the bottom, it goes through and flags the hydro and the wind and the solar units and just make sure that their cost codes are set to none, which is really just the default when it loads a raw file anyway. So everything's already set to none, but this just clarifies it, that those units will have no cost curve. Yeah, we can load that. And then we see that the cost model field has been changed for those units. And if we go to the display underneath the generators and then click on the linear cost curves, then we'll see the units that have linear cost curves or bid curves, and then they're associated. They each have 5 points and ascending cost model for those. So, and then the fuel type is set, so they're mostly natural gas. And for the limit monitoring settings, we want to only report limits in areas 3 through 7 and only at 100 kV and above. And of course, this will establish the list of possible constraints that the OPF tries to relieve, and we'll tell it to ignore radial elements as well. So going to the tools ribbon and then opening limit monitoring, we can make those adjustments by going first to the area reporting tab and initializing the report limits for everything to no, and then changing just areas 3 through 7 to yes. And then in the next column over, the report minimum KB, you can click in there and then just set everything to a constant 100. So we'll use the set drop down and then pick the first option in there to set all values to, and we'll just type in 100. And then those will all get set. And then the checkbox up at the top for not monitoring radial lines and buses, click that. And so with those filters, we can see from our summary up here that we're left with 7 lines of transformers that have overloads initially. So the OPF will try to relieve those. if I've got up here, it's set to just show violating elements, and I go to the lines and I can see which those lines are. So that's good. We can close that now. And yeah, this is what we've done thus far. And yes, we loaded these cost models already from that file. So I changed some of the data in there and set the cost curves. This is the display of linear cost curves. So the AGC hasn't been set. We could put that as part of our cost curve file also, but what's done here is we'll just load this from an auxiliary file because I don't want to take the time to go through manually creating advanced filters again. But if we load this file right here, I'll show you what's in it. It's got a bunch of advanced filters that look at different things for buses, generators, and areas. And some of the generator filters include ones that filter on the fuel type, so hydro, wind, or solar, or natural gas. And these fields were populated with our cost curve auxiliary file already. So we have that. We'll just load that, and then that'll enable us to select different classes of generators from our generator displays and then toggle the AGCs. We'll just load that. And anytime it asks if you want to create these filters, we'll just say yes to all. Okay, it modified also the display for generators. It added some columns on here. And then, so in any generator display that has the AGC field on it, which I think is pretty much any one of them, although actually we won't want to look at these because the cost curve type has already been set to none for some of them. So we actually will want to go to the main generator display that shows all of our generators here. And then we'll apply the filters. If the filter's already created, you can do that from the drop down filter toolbar right here. And we'll pick, for example, the hydro units, and then go to the AGC field and toggle that to no. And then do the same for units that meet the filter solar. And then also wind. We're just going to assume for purposes of this study that the solar and wind are not dispatchable at all. But you could certainly set up a study, where maybe you have maximum values that are loaded in, and then you allow them to dispatch lower than their max, but not higher. And then I don't know if there's any, there's none with unknown type, but we created a filter that's called unknown type that just, if the fuel type's unknown, then we could decide what to do with those. But in this case, everything's classified by fuel type. We'll just move the filter now. We took that step right there. And then, these are the steps that we just took with limit monitoring. Reported limits only on areas 3 through 7 and only at 100 kV and above. So at this point, our case is developed enough that we can solve an unconstrained optimal power flow, or we could even solve a constrained one right now. But we're going to take this step first so that we can use the results from this to establish a peaking price that we'll then assign to hydro units, and then assume that the hydro can be dispatched as needed to relieve constraints, but it's going to have a relatively high price because it's going to want to serve only as needed. So we'll go into the OPF options and results and make these changes right here, and then then we can solve it. Go to the add-ons ribbon and then open OPF options and results. and go to constraint options and just disable enforcement of lines and transformers and of interfaces, although I think the interface is kind of moot. I don't think they exist in this case. But if they did exist and you had limits and they were otherwise monitored, then you might want to disable them if you're trying to solve an unconstrained OPF. Yeah, at this point, I'm just going to open the message log and make sure that the process goes in an orderly fashion. And I'll click Solve LP OPF. We kind of purposefully introduced this issue here just to show you that it's something that could occur. If you have unenforceable area constraints, that means it can't meet the ACE equation. We initially had our case set up so that the ACE equations were met, but when it went through to redispatch the generation to try to get the lowest cost ones dispatched up to their max, which is really what it does in an unconstrained, then it changed the losses or enough, or it just kind of nudged the case a little bit so that it's not able to meet the ACE equations for two of the areas. And in this particular model, the issue would go away if we used a super area. But assuming we want to keep individual areas on control and keep the interchanges fixed, we might need to do something about this. And what we would need to do is change the unit commitment, either add units. If all the generators are at their max, then we need more generators. If all the generators are at their mins, then we need to take some offline. We'll look at those areas in just a second. Another thing that happens when you have this issue is that if we look at the LMPs calculated at buses in those regions, it defaults to 5,000, which is the hard-coded penalty factor for an unenforceable area constraint. So we see that in the Northern California and in the Southwest California areas. Other areas it was able to solve in a more normal fashion. We'll fix that. And the way we can fix it, one way, you could change the area zone filters, or you could put an advanced filter on only to look at those areas, or only to look at generators that have a high LMP at their terminal buses. But this way of looking at it, we're just using the area dialog and then looking at the generators within the area. So to do that, if we want to easily see which areas those are that are affected by this issue, we could go to under the optimal power flow group, look at areas. So we can see here the megawatt marginal cost average for the two areas is up high. And if I right click on one of these areas and show its dialog, then I can go to a list of generators. And I can see that the generators are generally, the ones that are AGC-able are all maxed out. So some of these other ones, like this is, either a hydro or a wind or a solar, it's not maxed out. But anything that AGC is set to yes, it's all maxed out. So there's, basically this dispatch caused the losses, must have caused them to increase, because then it tried to bring all the generators up. And so if we can just take a couple of, you can either sort by AGC, or I'm sorting here by max megawatt, and look for a unit that's offline and just put it in service. And then if we do, just change the status from open to closed. And then after you do that, you might want to just do a normal power flow solution to have it make sure that that'll converge. And then, yeah, that looks like it should be in good shape. It still says there's an issue here, but I think when we solve the OPF again, it should be okay. And then we'll need to go to that other area too, which I think was what, southwest? Is it south? Which one was the other one? Right here, southwest, area 6. So we can just find, with this dialog already open, we can just find. So, and then just kind of do the same thing, just find an AGC-able generator that's offline. We'll put that one on, and that's, okay, that's 800 megawatts. That should be plenty. And then just make sure the power flow solves. And then we should be able to redo the optimal power flow. So we could go to the add-ons ribbon and just solve the OPF again. And then you should get normal values in here. And then it should tell you also in the message log that there aren't issues with unenforceable constraints. And then you could also verify that on the LP OPF dialog by looking at individual LMPs or looking at the solution summary. This would tell you if there's unenforceable area constraints down here. This looks like a normal solution state for an unconstrained. Well, it's, yeah, there's actually just the 5 different area constraints are the only things that are being enforced. The individual lines and interfaces are being ignored. Yeah, this is kind of what we did right here. Another thing we can look at in the results in the OPF dialog is you can see the identification of a single marginal control. If you're only enforcing area constraints and not line constraints, then it's really just doing an economic dispatch. So like all the least expensive units that are needed are maxed out, and then there's one unit that's between its minimum and maximum limits, and that's the highest cost one that's actually dispatched, and that one's identified as the marginal unit. And see, I'll have to go, I closed my dialog, so I'll go back in here and then go to the bus marginal controls. There's a different generator in every area that's a marginal control, and let's see, the other display is the basis matrix. I think that's the one that's shown on the slide. And there's the 5 different area constraints are the only things that are binding, and then here's the marginal price, and then it identifies the marginal control for each one. So the next step that we'll do is we'll take all the hydro units and then just set them equal to the unconstrained area lambda, and that's going to be different depending on what area the hydro unit's in. But an easy way we can do this is just set the price to be equal to the megawatt marginal cost of the terminal bus of the generator. That works as long as the generators are located in the same areas as their terminal bus, and in this case they are. You could have a situation where a generator is in a different area than its terminal bus, and then I guess strictly speaking you might want to have different prices for those generators. In this case we can do it that way. So I'll go back to the Model Explorer and then go to first go to the generators display and then put the hydro filter back on. And then here we'll set the AGC setting to all the hydros will change to yes, because the next time we dispatch, we'll use those. So we'll toggle those to yes, and then we'll toggle also their cost models to piecewise linear for the hydro units. They were initialized as none. And then we'll go to the linear cost curve generator display. And then on that display, we'll also apply our hydro. There's also a filter called hydro study, which will also, within it, also have the areas, a filter on the area that it belongs to. It's kind of redundant in this case because the generators outside of California, we didn't identify their fuel types in the aux file. So the only ones that meet the hydro filter are ones that are in the study area anyway. So the two filters do the same thing. But what we can do here is we can set the megawatt value and the price value the way that we want to for just a single point, a single bid for all values of megawatts. And the way we can do that is we can set the megawatt breakpoint 1 equal to the minimum. So we'll just go into that field and then go to set all values to field. And there we'll find the megawatt output folder and then the megawatt minimum field. And then click OK. And then that gets populated. And then, yeah, now it defaults the bid to 0. But what we want to set that bid equal to the marginal price of the terminal bus. So we can go then just move over to that field and do set all values to field. And then scroll down to OPF and open that folder and then choose marginal megawatt cost of bus. Yeah, and then that gets set for everything. And then we can resolve the OPF, but this time with the enforcement of line limits. So to turn those back on, we'll switch back over to the OPF dialog. And under options, constraint options, and we can just remove these checkboxes here. I usually like to have the log open when I do that. But then it, solves LPOPF. It's moving around because it's trying to relieve all the constraints. It relieves a couple of them, but not all of them. So we'll take a deeper look at that. And if we look on the summary page here, your exact answers might be a little bit different depending on if you committed different units in that earlier step when we had the unenforceable constraints. If we go to our results summary, it shows that initially there were 7 violations that it tried to relieve, and it relieved 2 of them, and it also reduced the amount of overload across all of the violations. There's 5 that it wasn't able to clear. And we could contour this too to just kind of graphically see where these pockets are. I mean, you can look at the numbers in a table, but sometimes it's helpful to look at it on a OneLine diagram too. So if we switch back over to the OneLine diagram, we can see we have some constrained elements down here. And if we go to OneLine's contouring and then open that, it's actually all set. The one line was saved in a state where it's all set to go with the contour that we want for this example. So we're contouring the megawatt marginal cost and using this scale from 0 to 180. And if we just say yes, then if I go down to like the LA or San Diego regions, I can see like where those pockets are. And just some characteristics of line constraints. If you look at some of these, you notice that the LMPs are different on either end. On the sending end, it's a low LMP, and on the receiving end, it's a high one. We could browse these. One way to browse these is to go in the Model Explorer to the OPF branches display, just the lines and transformers, and we sort in descending order. Then we can see which ones are unenforceable, and they're all in the southern part of the system. Here's a binding one here, the one that's on the slide, this El Segundo. And if I right click on that and bring up a bus view one line, then I can see kind of what's on the, this is pie chart showing amp limits, so that's why it's not exactly at 100, but we can see on this receiving end we have a high LMP, and on the sending end we've got a low one, and actually a negative one, meaning if we increase the load here, then it'll actually allow a lower cost dispatch. The binding ones mean that the marginal controls are basically balancing it at its limit. And then this is the shadow price associated with it. And there's also actually this particular one-line diagram from the El Segundo 9 bus reveals that this generator's offline too. So putting this generator online would probably give some more options. It still might solve at a point where the line is binding. It may or may not, but we would expect that putting that on would cause the price to possibly drop or certainly not go up. Yeah, a couple of things that we could do if we wanted to explore the solution a little bit more. We noticed with the two areas earlier that had unenforceable area constraints that all their generators that were AGCable were pretty much maxed out. That's still the case. There is some room, there's enough reserve to meet the area constraints, but a lot of generators are still kind of forced to operate at the upper end of their ranges just to meet the load in the exports for each area, the ACE equation. So we could go through and add additional committed generators if we want. We could also see the effect of putting all of the areas into a single area with a super area and see if that relieves some of the constraints or lowers the prices or reduces the shadow prices. And we would expect that it would, at worst case, it would end up in a very similar spot, but it could also change the exports in a way such that lowers the cost quite a bit. So we can try that, and then we'll take a look at the unenforceable constraints that remain. To do that, we'll go to our super area display, and underneath, we can just grab the one underneath the optimal power flow in the Model Explorer. Or you can grab the other one too, it doesn't matter, the one that's under aggregations. And then we'll just right click and insert one. And we can just call it California. Since all the areas we want to add are in a range and we know what that range is, kind of an easy way to do it is just to type the range 3-7. then add those. And then we'll put it on optimal power flow control. Another thing we'll actually note, we would notice about the current system state, if we just go to our areas display, we should see that all of the ACE equations are still being met. It's still within the ACE tolerance for every area in there. And when we put the super area on, then none of those individual area constraints need to be enforced. The only thing that needs to be enforced now is the sum of all of the exports for all 5 areas. Just need to be met collectively by the 5 areas. So the ACE values here could float, and we would expect that they would, if doing so would allow for a lower cost dispatch. So if I open the message log again, and then go to the add-ons ribbon and tell it to solve the primal LP again, it's able to do some additional dispatch because it doesn't need to enforce, it only needs to enforce one area constraint for the whole super area. And you can see that the ACE values do move quite a bit. Some areas where heavy load and not much generation available, like in Southwest California, that became a net importer. And now also, if we look at the LP OPF dialog, it shows only 4 unenforceable constraints. So just the freedom to dispatch different generators in different patterns was such that it was able to relieve one of the constraints. Actually, one of the things that I did that's on the slide that I didn't do, and which we'll go ahead and do now just to make it more uniform, but if we're dispatching on the whole area, we might want to set a hydro price the same. I guess there could be reasons but why maybe you want to have different hydro prices in different zones or something like that within the super area, but the step that's shown on here is that we set a uniform hydro price across the whole super area. So I'll go back to just catch up with that step. We'll go back to our cost curve linear display in the Model Explorer, and I still have the hydro filter on here, so I don't need to change anything with that. I will go to the megawatt price 1, set that to, let's use 30. And then we can read the OPF. Things might move just a little bit, but yeah, they don't move much. The unenforceable constraints are more binding than the exact price of hydro is just kind of noise within all that. So there's really nothing that does. Yeah, we could recontour here too. And if I'll just keep this view right here because this is kind of where all the action is. And then I'll go to the contouring drop down and just tell it to recalculate the contour. I can see, yeah, I still have a little pocket here, but this is kind of shrunk. Okay, so if we wanted to take a closer look at the 4 unenforceable constraints that remain, we could look at the sensitivities, like the TLR sensitivities for each of those constraints, and just see, you know, what's going on there. Do we have generation that's maxed out? Do we have only high sensitivities at buses that have no generation or no load? What's kind of driving those unenforceable constraints? We might also look at adding constraints to our case through using Flowgate interfaces. You can model the flow on one or more elements with a contingent line outage element within the interface to model the behavior of a flow gate. And we could also look at varying cost curves and seeing what that does. To get kind of an easy look at sensitivities and constraints, we can first just check the LP basis matrix. And what we'll see here is that for some of the ones that have very high lambdas and that are unenforceable, some of the marginal controls that are balancing some of the other constraints actually have opposite effects on some of these. So, some increasing a particular generator might help relieve one constraint but make another one worse, for example. So they have opposite signs. We can see that if we just go to the LP basis matrix within the OPF dialog. So yeah, in here underneath solution details, we look at the basis matrix. We can see that for like some marginal controls, we can sort on the lambda in descending order. So that means our unenforceable ones are at the top. And we can see there's some situations where we have negative and positive values, and just generally very low values for a lot of these marginal controls too. So there's not much that the generators can even do to relieve those constraints. Like this generator actually has the biggest impact on this particular constraint, which is not unenforceable, but it's binding. And it has an 8% sensitivity factor on that. This one has only 1%. But most of these numbers are very low, and then there's some signs that are positive and some that are negative. So just kind of where it's balanced, there's really like nothing collectively that these marginal controls can do. You could run it all the way to the max or all the way to the min, and it's not going to do much of anything with the range being low and with the sensitivities being pretty low. 28791. We can look up and see what that is. 28791. So it's a marginal unit. It's in between its minimum and maximum. That's going to be another characteristic of marginal units. It actually could be pinned to a breakpoint. Other things we can look at, there's an auxiliary file that brings in calculated fields and custom expressions and things like that. And one of those is called PTDF impact. And we'll just load this file right here and then look at a PTDF calculation for this unit 29060. In order to interpret the signs in here, the positive or negative, they're also referenced relative to the from and to bus of the line, which is not necessarily the direction of the overload. So I guess that's something to keep in mind too. But with this custom expression, I think it flips the signs accordingly, depending on the direction of flow. If I go to load an auxiliary file and then look at this one, there is custom expressions and on generator levels, and then also for transmission lines, and it will look at the signs and put some logic in that, and then it modifies the displays, different object types. So we'll go ahead and load that and then just say yes to all when it asks. And then I'll go to tools, sensitivities, power transfer distribution factor. We want to pick up bus. So what we're doing is we're looking at transfers from this generator bus. This happens to be a marginal control 29060, and syncing it in the super area, California. Bus, and then find seller, and then if it's sorted by number, we can just type in 29060. And then for the buyer, we'll set it to the super area California. Then calculate the PTDFs. Then we'll look at the lines and transformers. This is filtered now on just the ones that have a non-zero shadow price. So the ones that are binding or unenforceable. And we can see, the binding ones are overloaded. And this PTDF impact, if we increase the output of the generator, some of these binding constraints are going to be relieved because they have sign in one direction, and some of them are going to be made worse. Signs in the other direction. So yeah, a PTDF impact of less than 0 means that increasing the output of this generator would reduce the flow. This particular marginal generator could help relieve 2 units that are unenforceable, or two lines that are unenforceable, but it would make another one worse. So yeah, I mean, just kind of globally, there's nothing that it can do to help the situation. And yeah, we can also do a multi-element TLR to kind of get some insight on what the issues are. And we can do that on selected lines. Pick the ones that are unenforceable, for example. So to do that, we can go back to our Model Explorer and then go to the OPF branches display, this one that we looked at earlier, where we've got it, we could sort it on MVA marginal cost and just pick the 4 that are unenforceable and select those. And then we can go to the tools, sensitivity, TLR. And we'll choose multiple element TLR. And we'll use the super area California as the, I think we want to use it as the buyer. So we'll look at injecting power at different points throughout the network and then withdrawing it at the super area. So it kind of mimics what would happen with our AGC. Selected devices, that's already picked here. And then we'll just calculate. And then if we switch to the generator display, we can sort in descending order on, say, the ETLR, which is it's just the sum of all of the TLRs with the sign of the value flipped depending on whether or not the flow is going from the from bus to the to bus or the other way around. So it's actually picking up the impact of whether or not the flow is being made worse or better. And positive values on a committed generator indicates that decommitting it might help with the collective overload. But some of the sensitivities on some of the constraints are really low, and on some of them it's high. But we can sort like that. And if you have a negative value on a decommitted unit, that means that committing it might help. So we can bring these fields here onto the generator display also. And I think actually the auxiliary file that we might have already done that. I'll just close this out and go under the Model Explorer, just under the regular generator display. Yeah, so it has the ETLR field is brought on, and then also there's this calculated field called ETLR potential. If we sort instead on ascending ETLR, let's do that. And then these negative values, this kind of indicates that committing these units might help. We could also put them on fast start, but these have piecewise linear models. This is a unit that's not dispatchable. I wonder what this is a wind turbine, so it's going to be stuck right where it is unless we make it AGCable. But we could take the units in the top 20 that are not already committed with the negative values right there and see if that helps. Yeah, these are all piecewise linear. So just like basically down to here. And then once we commit those, we might want to at least make sure we can achieve a regular power flow solution before we go any further. So if I go back into the OPF options and results, I can see what happens if we do a solution here, and we still have 4 overloads. The MVA sum is now 36. Other things we could do is we could flip the sort on that and try decommitting some of these units, say at Long Beach, and see if that helps. So I'm going to leave this open right here. Oh yeah, so yeah, this shows, I guess, the initial violation. It relieved 4 MVA of overloads, but still has 4 unenforceables, probably the same 4. So if I flip the sort on this the other way and say, let's open these Long Beach units, because maybe they're doing more harm than good. Then we'll solve the power flow, and then solve the, yeah, that doesn't really do that much. Yeah, another thing that we can do, I'm going to skip that next step because I'm in a slightly different state than what's on the slides. But another thing we could do is we could sort on this custom expression called the ETLR potential, and I'll go back to the Model Explorer and do that. Or maybe I need to recalculate. Let's do that. I'm going to go into the TLR sensitivity. Actually, it might not change that much if I'm still looking. Just recalculate those. So yeah, I just went into my TLR sensitivities and then just recalculated them with the same selected devices. I'll come back here and then just, grab like 20 or 30 units or so, make them fast startable. So then I'll go into the OPF dialog and then make sure for control options that I'm allowing commitment and decommitment of fast start units. That's actually set. It might have been loaded with one of the auxiliary files earlier. Then we can try solving the OPF again. Yeah, and if you look at the generator OPF display, it will tell you there. I think you can also look in the solution details inside the OPF dialog, but it will tell you on this display under optimal power flow generators, it'll tell you if certain units were turned on or off by the OPF. We could recheck our color contour. I'm going to switch the view back to the whole state. Yeah, so we have fairly uniform pricing, except for there's still pockets down here. Yeah, if we look at the San Diego area with the dynamic formatting too. Yeah, if we turn some of these layers off, it kind of declutters the display a little bit. And you can see that boundary a little bit. So I turned off always visible, dense, sparse, and very detailed. Just left these three. And then what we can do with our dynamic formatting to what's described on the slide is you can still have it show the lines that meet this dynamic formatting. So if we check the forced visibility box there, then it shows those. So we've got, yes, these unenforceable constraints here that are right at or kind of span the boundary on this pocket. One thing that we might notice too is that if we sort on the negative ETLR right now and we look at buses, then we can see that a lot of these in the Southeast California area, are most of them are either have no load or generation at them or have load only. The first generator that we get is this Campo one that we saw earlier, and it's a wind generator, so it's not AGC-able. And so this kind of suggests that because the highest sensitivities are only at load buses, it's something of a load pocket. We could see some changes if the load were curtailable, or we could also just conclude that we're going to have a pocket there of high prices because of that load and some unenforceable constraints. But we can also look at loading in some load benefit models and making the loads as OPF controls. What I can do, yeah, if I go to my Model Explorer and go to buses and sort, kind of the phenomena that's described on the slides is visible here. If you sort on the ascending ETLR, this is saying that, you know, increasing generation injection at these buses would be helpful for the basket of constraints. But there's no generation there until you get down here, and that's a wind generator. And then you keep going, and you don't see any other generators. I don't know, this might be wind too, but now the sensitivity is getting lower. So we could try to see what the impact would be of using load benefit models and demand response at some of these loads. So if I go up and load an auxiliary file and look at the one called California Load Benefit Model. And what this does is it adds these 4 loads that are in this area. And let's go ahead and load that. Let's look at them up here, actually. Here it is, under network loads, benefit curve there. If we sort on benefit, it shows everything, even the ones that have none. Yeah, the load benefit curves are descending the first megawatts have the highest value, and as the load value goes up and up, then they have less and less marginal benefit. So we would expect that if these get dispatched, that they would get dispatched probably along one of these breakpoints. Another thing that we need to do is make sure that the individual loads are AGCable, and I think that happened with the auxiliary file. Yeah, so the auxiliary file loaded these and then set the individual loads AGC field to yes, but then we also have to enable that at the area level and in the OPF options. So if I go under optimal power flow and go back to the optimal power flow areas, there's a load dispatch. And this is all set to no, but it's also grayed out. And if you mouse over it, it'll tell you it's grayed out because it's also disabled in the OPF options. But we do need to enable it in both places. So we'll enable it here. You can enable it everywhere too, I guess, if you wanted. It wouldn't really do anything different. But for areas 3 through 7, we would want to make sure that we at least enable those. And then also go to the LP-OPF dialog and under just common options, decheck the box that says disable load megawatt control, and then resolve it. We can look and see like what the actual control changes were on the loads, and there's a couple different ways we could look at that. We could look at underneath loads benefit curve linear, and we can see there's a difference from some of these loads between the megawatt output and the max megawatt output. Just sorted that wrong. It's not very big in most cases, so it didn't curtail a whole lot. If we go to the LP-OPF dialog and we look at, yeah, we can look at the LP variables. We'll just look at all the loads together. Yeah, they're down here, so the generators are at the top and then the loads. We can see that just a few loads were curtailed by a little bit. But that's enough to relieve most of the constraints. And we can see a lot of them are at breakpoints, so they're not actually marginal controls. Yeah, it's really just still the generators that are marginal controls, but some of the loads settled off on breakpoints. Yeah, the basic variables are still just generators. But if we go back here to this display, now we have just one line in here that I think that's binding. Yeah, let's just recontour. So we'll come up here. These are anything that's either binding or unenforceable. Yeah, recalculating the contour, that little pocket just goes away. I still have an unenforceable one, it looks like, in the LA area. This is not unenforceable, this is just binding. Otherwise, there'd be a bigger gradient right there. But it makes that little pocket disappear. Yeah, if you get rid of the pocket in LA, then it looks much more uniform. Yeah, in this example, it just took a 30 megawatt reduction in load. Okay, so next we'll look at adding contingent interfaces to our solution, and that'll add, of course, more constraints than when we had just the transmission lines themselves. We'll come over here and just go to the load auxiliary, and it's the one called California contingent interfaces. And I'll just, again, open it here in the text editor. They each have a branch and a branch open element. So kind of similar to what we did in the SCOPF section with these. Although we just looked at one of them on the 7 bus case, but we'll load several of them. The confirmation dialog, just say yeah, all. This option that we looked at yesterday in the simulator options is also available on the OPF branches display. This option to monitor and enforce contingent interface elements in the power flow and the optimal power flow, but not. So that second option is what we want in this application here too. And if we look at our list of interfaces, now we see that we have 20 of them. And we want to make sure that we get a power flow solution that does incorporate those as we want it to. Yeah, it does. It should tell you at the bottom that it's updating contingent interface flows. And if it does that, then we're good. And it would show, so then if we look at all of these are now overloading. So we're going to have to try to dispatch around those. But if I look at, say, a specific one, it should also show in here a non-zero flow for the contingent element as well as the monitored element. So they all have limit that were set when we read them in from the auxiliary file. So this is what we did this step right here. If you go in to change it in simulator options, then it's helpful to close it in the Model Explorer, like not have this open when you go. Sometimes if you change it in one and the other one's open, then it doesn't really change. We're only changing it here. We'll go to I'll go back into the OPF dialog here and then go to back to the solution summary. And now we might see some values populate for interface constraints. We run this, so we'll hit the solve LP OPF. And I meant to open the message log too. I usually like to see that. It's better than just. It's got some unenforceable ones, and it's trying to. It looks like it might be bouncing a little bit back and forth between a couple of different solutions, in mine, but it eventually kind of times out of that. So yeah, we still have the unenforceable line constraint. So most of the interfaces it was able to relieve. But if I go back to my OPF constraints display for the branches and the interface, I can see which ones were relieved and which ones were not. Your list might be a little bit different than mine. Anyway, that's kind of the end of that example. There's a section in the back that it talks about other possible issues that can come up during OPF. A lot of these have to do with reactive power flows and voltages and taps and stuff like that are kind of, more with the power flow solution that's kind of out of whack than the OPF itself. There's no hands-on example really that matches this. Well, actually on some of them there are, but we generally just kind of describe it on the slides because some of these are kind of rare, but just things to be on the lookout, especially if you're using the AC power flow solution. If you're using DC, a lot of these issues don't crop up at all. In the examples that we've taken so far, we've always ignored radial elements, but this just kind of shows that if you leave them in there, some of them that are overloaded will always show up as unenforceable constraints, especially if there's either no OPF control on the other end of it, or if the rating of the radial element is such that it's too low for what it's connected to, which would just be like a bad data thing. But normally you would just not want to look at those when you're trying to sort through the results. So we actually did look at this example in our California, where we had two of the areas didn't have enough generation to satisfy the ACE constraint, so you get the $5,000 penalty cost associated with it. We saw that in our example. And then also, if you're using a really wide area and the starting point of your case is very, very different from where the OPF wants to dispatch it, then you can end up with trying to move too much power across the network and having a convergence problem or hitting a PV limit, and then it blows up. But with the DC, it generally doesn't. Yeah, this is just the example right here. It's similar to what we went through before. We end up with a bunch of unenforceable constraints initially. On this one, a lot of them are radial. So if we don't monitor radial elements, then a third of the unenforceable constraints just kind of go away right away. So that's just, we ignored them from the get-go in our example, so we didn't really see that. You can also have some issues if you're looking at your unenforceable constraints and you don't expect some of them to be unenforceable, or it looks strange or unusual, you haven't seen those pop up before, you might want to look at the reactive power flow on the line as well as the megawatt power flow. And we didn't really do that in our example, but if we bounce back here, we can go to our branches display, and it normally shows you the MVA flow because that's normally what the limit is based on. But you can also just go to the display column options here and look at how that breaks down into real and reactive flow. And again, if you're using the DC, then it doesn't really matter so much, but we could grab the megawatt value under megawatts and the megavar value, megavar maximum under megavar, and then show those as well, and just see if there's anything kind of unusual. Actually, this one's a little bit unusual right here. It seems like the power factor on that line is kind of low. Most of them, it's pretty high. So the megawatts is pretty close to what the MVA is. This one, it's quite a bit different, and there's almost as much megavar flowing on it. So it's close to like a 45-degree angle. This one's not too bad, but it's worse than the other two. So you might look to see if there's like a transformer tap issue with that. I don't know in this one what we've got going on. In this one, we've got a capacitor bank right here, and then also these generating units are also producing a lot of VARs. So there's some sort of voltage control issue going on. There is a tap changing transformer right here. Yeah, it doesn't really look like there's taps in parallel. The slides describe a situation where if you've got transformers that are in parallel, but the taps aren't balanced, then you can get circulating reactive power where it's going in one way and out the other. And if you just balance the taps, then most of it goes away. You try taking this offline. I don't know if that's going to cause this to blow up or not, but the overload goes away on that. The voltage still seems kind of reasonable, but it's still missing the target. So it might just be kind of a faulty set point, or maybe, well, this voltage kind of dropped here too, I think. So, but anyway, it's kind of a voltage related overload. We still have a pretty high, or rather a pretty low power factor on this line. The megavars are pretty close to megawatts. There's a big difference there, but it's not overloaded anymore. that might not be, if we solved it again, it might not be a binding. Yeah, that one kind of went away. Yeah, there was a reactive power issue there. But in this particular example that's described on the slide, there's some tap ratios that are out of whack. And if they're initialized, all at a value of 1 and then resolved, then the reactive power flows drop quite a bit. The power factors go up on a lot of those elements, and you don't have overloads. Again, this is not something, if you use the DC power flow, then this kind of goes away because it doesn't worry about trying to enforce voltage at that point. So if you are using the AC power flow and you're seeing these issues with high reactive power flows, we do have a tool on so it's under Tools, Connections, Find Circulating Megawatt or Megavar Flows. And we talk about this, I think, a little bit more in our security course, but you can just set this up. You can just run this on the default values right here, and then click the Find Cycles button. And actually, yeah, it does identify that there might be some tap issues. Maybe this is an issue that's contributing to this. We have a bank of transformers right here, although they look like they're fairly close to balance on these taps right here, but there's a lot of reactive power flow going through here. You can look at these. Oh wait, 1.1 and 1.01. Oh yeah, okay, those are different. I wasn't seeing the extra 0. It looks like 2 of these are on LTC control, and then others are fixed. And on some of these transformers, there's negative megavars, and other ones there's positive ones, which is kind of funny. We can try balancing out. There's only 2 of them that are on. I think these are just the controllable ones, or maybe not. No, those are. We could try moving them all to 1.0187 or something like that, just like making these values be the same. And then, oops. I think we need to close that because it's a modal dialog. And then try resolving. Yeah, so that helps quite a bit too, I think. But while they're still, these are still different. It might make sense on these transformers if we take them off control. So yeah, this is kind of funny because there's five transformers in parallel, and 2 of them are on control and the other ones aren't. The other ones are fixed, it looks like. So this one, yeah, this one's not automatic control enabled. We could just try moving all of the taps in here to the same values. Oops, this should be 1.0187. And I'll just leave this dialog open and then save it, and then I can thumb through. Yeah, or you can copy from one and then paste in the others. So yeah, this is an issue that was affecting one of our overloads here. Yeah, if those are all balanced, you still have some reactive power flows through here, but it's a lot better than it was before. So I wonder if that even becomes a binding line anymore. If we balance those, it might even go away. it does. There's also phase shifting transformers can also behave in strange ways, especially if you've moved the load around in the case, if you've like increased it or decreased it and not changed the phase shifting transformers. There's an option to kind of punt in the OPF if you're not really sure where they should be set. And you can do that by putting the phase shifting transformers on OPF control and allowing the OPF to optimize where they're dispatched. So when you do that, it usually ignores the set points and just uses the angle minimum and maximum as a full operating range and just picks a point where constraints are relieved and you get a more optimal dispatch. Kind of the danger in doing it is that it could dispatch to a place that makes the power flow solution kind of unstable, because usually phase shifters exist to divert flow away from weak parts of the network, or they might also exist to minimize circulating megawatt flows. And actually with the circulating megawatt flow problem, putting them on OPF control might actually help. But if it's a voltage issue where a phase shifting transformer is trying to keep flow off of a weak part of the network, then this could cause a failure. If you're using the DC mode, there's no danger of collapse because of bad phase shifting transformer set points, but you still could end up kind of at an unrealistic, I guess, dispatch. But what you can do, and then this slide just kind of describes, you might want to still enforce regulation limits, or you can also ignore them. But it has one that's in California. I guess it has some that are, okay, it has a few more, I guess, that are not in California. Actually, some of these phase shifters are fixed, but you can put them on control. You can also put them on OPF control. So that's under here, under the XF auto field for the individual. And if we wanted to just let the OPF control all of them, we could do that. Then we also have to enable control at the area level. And this just says that it's not. If we toggle this to yes, actually only one of them is in California, this one. So these won't matter because they're outside our area. It's not on a tap limit. It might be on a regulation limit. Let's see, automatic control options here. Yeah, it has a power flow minimum and maximum of 2,500 to 2,800, and it's currently at 26, so it's within range. It has no error. But if we put it on OPF control, then what it could do is it could operate within this full phase angle range from minus 30 to plus 30 and violate this regulation range. But it could do so if doing so would help relieve constraints or lower costs, then it could do that with it on OPF control. So other things that we have to do, we have to allow on an area level, if we want the phase shifters to be on OPF control, we have to change for the area the control setting to yes. And actually we did that for this area on the other dialog where we were looking at individual devices, and we changed the individual device to yes. We also hit the area field right here. So what that did was it changed this to yes for all of the areas that have phase shifters. And then the other thing we have to do is on the OPF dialog globally, we have to make sure on, I think, common options that we're not disabling phase shifter controls, and that's the case here. So that's good. And then the other thing to look at or to consider is you might want, I'm going back to the phase shifter display here. If we look at this one, like the one in desert right here, for example, which is the one that's in our area, I think there's also a checkbox on the OPF tab in here to enforce the megawatt regulation limits in the OPF. And this is optional. If you check this, it'll still try to stay in this range. If you don't check this, then it'll use the degree tap limits, which are, for most of these, is plus minus 30. So I think initially I'm just going to check that, see what it does. And then we can resolve the OPF. And see if this guy moves at all from minus 6.1. It did move. It's now at minus 4.6 degrees. If I go back into the dialog, I go to the transformer tab and then the automatic control options. Yeah, it moved it to the lower limit of 2,500 megawatts. So you can also tell it to not enforce those. But if you do that and the range is really wide, it could end up pushing it to an unstable part. I'm not sure if it will with this case or not. Let's just see. I moved it a little bit to minus 3.9 degrees. So now it's outside slightly of the 2,500 to 2,800 megawatt regulation. Again, I guess you can do that to try to find if it doesn't move it outside, it's going to do it to either relieve constraints or reduce cost. Actually, they're kind of one and the same. It's going to come to a better value for the objective function in the OPF, but it might kind of violate some stability limits if the phase shifter regulation range was kind of set up to do that. You can put them on OPF control, and then within doing that, you can optionally choose to enforce or not enforce the megawatt regulation range for individual devices. So just different ways you can try to optimize. This graphically shows in the old case that we used to use in this example, there's a phase shifting transformer that's in series with another transformer. And the phase shifter was actually regulating to a range of 60 to 73 megawatts, but the limit on the transformer itself and on the transformer in series was both in a range that was less than 45 megawatts. So just kind of by design, it was violating its own limit and the limit of the transformer in series. We might just ignore those overloads and tell it to not monitor, or we might allow it to dispatch itself down outside the regulation range using that OPF option to do so. So it just really depends on whether you decide that that's a bad limit or if it's a bad regulation range. And then the rest of this example kind of goes through some effectively radial elements and some load pockets. This is a depiction of part of the system where you have a generation pocket in here and lines that aren't recognized, strictly speaking, as being radial, but they're very radial in the sense that they depend on the output of these generators. And if the rating on the element is lower than what it needs to be in order to support all the generation, then you kind of have to ask whether or not the ratings are bad data or not. But the fact that you have overloads on both sides of this kind of suggests that maybe it's just bad data, that it should be able to support all this generation. there's really just one of two things you could do. If you wanted to see this constraint go away, you could take some of this generation offline, or you could just ignore the overloads. So, I mean, one of those is probably true. Either if the network really does have these limits, then it can't simultaneously support all of these generators. So some of them could be turned off, or you just ignore the lines. This is a different situation where these two loads are at the same substation, and I guess this is supposed to be some sort of breaker or some sort of tie, but it has a really large impedance, which could be bad data. Maybe this is supposed to be closer to zero impedance to represent a breaker, but the effect of this being a really large impedance and these others being relatively small impedance means that this looks kind of like a radial line. Not much flow is going between here, and you have a load at this bus. So that load mostly has to be fed on this line. So it's causing an overload here because of the limit on this line and the value of this load. So you could ignore that limit perhaps because it's effectively radial. Or you can just open this guy and then ignore it. This is another unusual situation where there are negative loads in the case. And I'm not sure what that's supposed to represent. If it's supposed to represent a generator, there's negative loads here, and then there's positive loads at this neighboring bus. And the values are very similar. Like you have two negative 32s over here, and then you have a bunch of 64s over here. And you could take one of the 64s out and then remove two of the negative 32s, and it wouldn't change the net load, but it would very much change the flow that's going across here, because it looks like you have a generator here and some loads here, and most of that's taking the direct path across here and overloading these lines. You could just ignore that line, or you could take these two off and take one of these off. And the net load in the area would be the same, but the flow going directly across would change quite a bit. In this particular example, once all those things are either ignored or fixed, then there's just a few remaining loads. And kind of like in our example, these are tied to a load pocket, which we saw in the San Diego area. In this case, if you draw kind of a one-line diagram that's in the region of these binding constraints and contour that, then you see that there's a bunch of load kind of inside this. Well, this isn't a contour, this is the background shape right here, but there's some load inside this region. There's one generator in here that I think might be offline. So this load has to be fed through just a handful of points, and some of them are at or near their limits. So yeah, we end up with very high loads. And if we contour it, it looks something like this, which is similar to what we saw in our case in the San Diego area, where there's a pocket here of high prices and low prices outside there. Just kind of the summary, things that might not make sense might be due to high reactive power flows. They might be due to phase shifters that are on settings that don't quite match the load or don't quite match the ratings of lines that they're in series with. You just might need to use some judgment to either ignore or relax constraints, or just remove things that look kind of funny.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.